Reminder, I would like to let you know that this particular session will be recorded, and a recording will be sent to your email for all registered attendees. So again, this is the brief agenda that we have for today um, regarding the presentation, which is titled Simulation of Bistable Actuators in SolidWorks. Now, a little bit about EMWorks as a company. EMWorks has products that are gold partner products to SolidWorks. We have two particular products, EMS for SolidWorks and HFWorks for SolidWorks. It is the number one choice for electromagnetic simulation for SolidWorks users. Okay? And we have over 500 trusted customers worldwide. And as you will shortly see in the demonstration, EMS is extremely easy to use. It has the same philosophy and principle as the SolidWorks CAD. Its workflow and user interface is very familiar and to a SolidWorks user. And as a result, people usually have a very short learning curve to learn this program. Now, one can take a look at the products and bundles that are offered. Now let's focus on the EMS product. That's the low frequency product, and the product where we will focus our attention today for this webinar. Right? We have 6 different types of capabilities or solver capabilities in EMS. Those are the electric modules, which comprises electrostatic, electric conduction, and AC electric, and also the magnetic modules such as magnetostatic, AC magnetic, and transient magnetic. Now you can purchase each module separately, and there are also some add-ons that are available for some or all of these modules. You can couple them to a thermal simulation, you can couple these modules to a motion simulation, or you can couple them to a structural simulation. All of these can be purchased additionally as an add-on. Now we offer both activation as well as network license. EMS comes standard with activation license, and for an additional fee, one can upgrade to a network license. Now EMS Premium is an amalgamation of all we just discussed, which is a part of EMS Professional and all the add-ons. And obviously, if you are using more than 2 or 3 simulation types with add-ons, EMS Premium might work out to be a better option. Now, there's another program called HFWorks, which is mainly a program used for designing and simulating passive RF and microwave components in SolidWorks. And it has 3 different simulation types: resonance, S parameters, and antennas. And we have a lot of webinars dedicated to the high frequency side of our product. And I request you to look into our website to find more information about this product. Now just let's take a product-wide application for our EMWorks products. On the left, you can see our low frequency product, which is the EMS for SolidWorks. And basically anything that varies from DC current all the way to few megahertz can be simulated using EMS, right? So EMS caters to several key industries and applications as outlined here. Some of the major industries that we play a role are in the actuators, motors and generators, loudspeakers, magnetic recording devices, and levitation devices, serving mainly transportation, automotive, defense, aerospace type of companies. We can also simulate coils, permanent magnets, NDT devices, sensors, etc. that can cater to several key industries in the consumer goods, energy, and industrial processes. In the power electronics, you can do standard power electrical machines such as transformers, inverters, converters, etc., inductors, and so on. And they feature in energy and electricity generation, those kind of industries. And finally, when you talk about the high frequency product, which can range from a few 100 megahertz all the way to several gigahertz in wavelength frequency. And passive RF and microwave components can be designed using the HFWorks product. Mainly, people use them to design antennas, both planar as well as horn antennas. You can also do problems related to multiplexers, filters, couplers, etc. Mainly RF, and also study resonance of these passive RF and microwave devices. And they mainly cater to the industries such as aerospace, defense, and electronics, the high-tech electronics of today. Now let us move to the topic that we have for today, which is the bistable actuator. As the name suggests, a bistable actuator is something that has two stable positions. I would like you to pay attention to the diagram or the image that I have on the left-hand top corner. Now here is a section view of a bistable actuator. It has a coil and it has a permanent magnet, which is a radial magnet, and it has two positions. The lower position is what is shown here. Once it is at a particular position, it gets locked to that position thanks to the magnet and the magnet circuit and the circuit that is provided here. Now, to be able to actuate this actuator, or with respect to this particular image, for this actuator, this white color piece that you see here in the middle, for it to be actuated up or for it to move up, one needs to apply some kind of excitation in the coil. And when you apply some current, then there is a force acting on the actuator that is greater than the holding force that holds it on position. And that particular force is going to aid in the actuation of this device. I would say this plunger, and it will go to the top. And once it goes to the top, then a similar holding force appears even when you remove the excitation. And that's really what we will study here. Right? So there are several objectives that one can accomplish by studying these bistable actuators. For example, people would be interested in computing what is the holding force at each of its position and what is the response of the actuator itself. So basically, how long does it take for the actuator to actuate? And how does it change when I change the type of excitation from, say, a constant DC to some kind of a pulse type of excitation also. So one will be able to study the various things like this. And also, one can understand the flux distribution, as you see in the lower left image. You can understand how the flux path is through your actuator, what is the magnetic circuit, and so on. So with this, let me jump into SolidWorks, where I can use a real bistable actuator for micro actuation devices, and I can tell you how it is done in EMS. And we have, as I stated earlier, we have several objectives for this simulation. The first being, I would like to understand the forces acting on the actuator itself. The second thing is I would like to understand the response of the actuator under a particular excitation of the coil. How long does it take for it to travel a particular distance? And once it travels a distance, what is the locking force? And finally, what happens when I change the excitation? Does it still actuate under a given time frame, and so on? So for this particular micro actuator, it is desired for the actuation to happen within 5 milliseconds. That's really the design parameter that we are using to design this actuator. So let me go ahead and quickly change to the SolidWorks. Yeah. So as you see here, this is a section view of an actuator, bistable actuator. So if I take a section view, it becomes very clear. So a quick look at some of the components. Then we have the the outer component that is magnetic material that's made of some kind of a steel, and that really acts as a magnetic circuit. Then we have the yoke material that is also a magnetic material made of steel usually, and this is the one that actuates, and you can actually connect it to a shaft and you can make that actuate. There is also the coil as you see here. Now this is a wound coil, and this coil is important because only when you energize the coil, the actuator will actually actuate from one position to another. And once you stop the current in the coil, the actuator locks on to the position that it reaches. Then finally, there is a radial magnet that forms a very important part of this actuator design that completes the magnetic circuit. Okay. So the actuator is free to move inside as you see here. One can actually move the actuator inside as I am dragging. As you see here, I can move my actuator up and down physically in SolidWorks because they are mated that way, and I would like to do that. Now the objective of the simulation is what happens really when I apply an actuation, some kind of excitation in the coil, how much force is being acting on the actuator, and how long does the actuator take to actuate a distance of I think is 5 millimeters or so. Yeah. Okay. So now this is a coupled EMS and motion simulation. So our motion engine will be accomplished using SolidWorks motion. So if I direct the attention towards SolidWorks motion here, we set up a motion study and we apply a force acting on the actuator, actually the yoke, as you see here, and we apply a force equal to 0 newtons. Now a force of 0 newtons basically tells the program of SolidWorks motion that an external program like EMS will actually give the real force acting as a function of time, and this will help SolidWorks motion to move the yoke. So as far as the setup in the motion is concerned, one needs to define this dummy force which acts as a placeholder, and finally we need to tell the program how long we want to simulate this. So, and that's done as I mentioned earlier. We would like the actuation to happen within 5 milliseconds. So I would like to study what happens in a time frame of 5 milliseconds. So we have a total time of 5 milliseconds. We want to study what happens to the actuator. Now when come to EMS, there are several steps required for the EMS product to do this type of simulation. So the first step that is required to do a simulation is called setting up a study. So one can set up a study. We have several different study types in EMS. Because this is a combined motion and EM simulation, where the position of the yoke is going to change with respect to time, I would resort to using a transient magnetic type of simulation for this particular application. We have other types of simulation, as I mentioned earlier in our product bundles. We have the magnetostatic, we have the AC magnetic. So depending on what your excitation is, one can do different types of simulations. As far as coupling to concern, this is coupled with the motion simulation. Here I'm coupling it to the motion study 1. Now here automatically EMS works hand in hand with SolidWorks motion to do this problem. So once you create a study, it creates a study tree as you see here. In this study tree, we have all the materials that we need to apply to the different components. So for example, the coil is made of copper. To apply material, you go to the particular component and select apply material. EMS comes with its own material library that is fully customizable and that contains all commonly used electrical materials. So you can select from the conductor, you can select copper and apply the same. And then the outer shell and the yoke, they are made of magnetic material, in this case steel 1010. EMS library contains a lot of commonly used steel. Let's go ahead and take a look at it one more time. which has its own magnetic properties as well as the BH curves and so on. So if you want to create your own material, the EMS framework provides you an option to create your own material, and you can even apply the magnetic properties like the BH curve, electrical conductivity, and so on to your material. And finally, the radial magnet that forms a very important part of this magnetic circuit that enables the functioning of the bistable actuator is made of a neodymium magnet N4212. And once you define the magnet, you need to define the direction of the magnet, and that is done using what is called as the coercivity direction. Now, as I said, this is a radial magnet, so we can use a cylindrical coordinate system to define the radial magnet. So I've used a cylindrical coordinate system, and the magnetic polarization or the direction of the magnet is radially outward. As you can see here, you use the cylindrical coordinate system, and this is along radial direction. Okay. So once you have defined all the components and the various parts, it's now time to define the coil. So now I'm going to assume that the bistable actuator is right now in its lowest position, as you see here. We would like to apply a coil, an excitation in the coil that will produce a magnetic field, and this magnetic field will create a force on the yoke, and this force hopefully will overcome the holding force that is holding it down, and which will cause it to actuate. Now, how does one define a coil? So to define a coil, one needs to select the components that comprise the coil. We have to select the cross-section face through which the conductors are there. It's actually wound coil. And here you can select the number of conductors that go through this cross-section area. So we have about 120 conductors, 20 wire gauge AWG 20, and that gives a filling factor of about 87%. And then finally we apply a DC current of 10 amps. So right now we just want to know if 10 amps will be enough to actuate this actuator and enable it to move the 5 millimeters or I think it's 4.5 millimeter travel within 5 milliseconds. So once we do that, then we request the program to calculate the force acting on the yoke, and this particular force is transferred to the SolidWorks motion, force 1 that we set up, a dummy force that I showed you earlier. So this force is transferred to SolidWorks motion. So with this, we come to an end of the setup as far as the setup is concerned. So I have run this problem prior to this webinar. So let us jump straight into the results and take a look at some of the simulation results. So the first thing that I'm interested in is, as I said earlier, is the response characteristic. Now we can study the force acting on the yoke. For example, at time equals 0, we can see how the minimum force is about 8.5 newtons due to the excitation. That happens at time equals 0. We'll see if that is sufficient to overcome the holding force. Okay. Now you can see this is how the force varies as the actuator actuates. And also one can take a look at how the center of mass of the actuator moves. So you can see here under this constant DC current of 10 amps, the center of mass actuates to about 5 millimeters, which is the travel, and it achieves that in about 4 milliseconds. So we have achieved our outcome of actuating this particular device under 5 milliseconds using 10 amps. So we can study this. So let us also understand how things happen from a magnetic circuit perspective. So here is a section plot of just a section plot of the magnetic flux density. You can see here how the magnetic flux density is distributed in all the components. And because this is a coupled motion simulation, I can animate this, and you'll be shortly seeing how there is an animation of this yoke as it moves from the bottom to the top in 5 milliseconds, in under 4 milliseconds. So this is the animation of it. So what happens is, as you apply an excitation to the coil, it overcomes the holding force and the actuation actually happens. It moves up till it reaches the ultimate point of its travel. And you can also take a look at the vectors as you see here. So let me go ahead and go to the vector options and fill that. Now this is really the vector plot. Now this shows the field lines and flux lines at time equals 0. This is really how the flux is distributed. So you can see the magnetic path clearly here, and I'm going to animate this as well, and you can see how the flux varies as it moves up. So as you move up, you can see variation of the flux. Okay. So I think it would be nicer if I turn on my air region as well. Take a look at the same thing, and now under this I'm going to animate them once again. Now this will be very clear how the flux lines and the flux arrows moves as you energize the coil. So you can see that there is a need to complete the magnetic circuit, and that pushes the plunger up and so on. Okay, so now one can also look at the velocities and the accelerations. So you can take a look at the linear velocity plot. So you can see here that the maximum velocity that is reached is about it's about 2. So the maximum linear velocity is about 2.83 meters per second. And then once it reaches its maximum travel position, then it's kind of forced to stop. So the velocity gets back to 0. Okay. So one can study the velocities, one can study the accelerations, etc., to really understand how the motion behaves. Okay. So so as far as our objectives are concerned, we have understood that when we apply a 10 amp current excitation, we will be able to actuate this in under 5 milliseconds. But imagine that this micro actuator works many times. It needs to be actuated hundreds and thousands of times during a day, and it needs to be it's something that's doing a process simultaneously non-stop, and it needs to be actuated many times during its lifetime. Okay, so under this scenario, an engineer might be thinking, well, what happens if I apply a constant DC current? I'm actually losing a lot of power for actuating this. Now, can I have a more efficient way of actuating this? So if you want to make another study, so EMS allows you to do several simulations for your same model. Now this is another simulation where I'm going to actuate it using some kind of a pulse excited. So instead of having a constant DC current, I'm going to have a pulse excitation where the current reaches about 10 amps and it stays there for close to 2 milliseconds, and then it's pulsed back to 0. So when I have this kind of excitation, obviously I save a lot more power in exciting this particular bistable actuator, and over a period of millions of operating cycles, you can see substantial savings in power. And that's one of the objectives of studying what happens under this kind of excitation. Would I still be able to actuate it under 5 milliseconds, which is a design requirement? So let us quickly now compare the results here. So I can again take a look at how the center of mass displaces. Now you can see here, instead of 4 milliseconds that happened before, under this actuation condition, I can actually actuate it somewhat around 4.5 milliseconds, but still we have achieved the actuation of 5 millimeters under 5 milliseconds, and we have considerably reduced the power required to actuate this. And you can see these values of the center of mass motion. And also you can select the force here, and you can see the force acting. So at time equals 0, when there is no current, if you remember, we have a pulse actuation. This is the holding force in the minus y-axis. So the holding force is about close to about 5.7 newtons, right? And if you remember, when we actuated using 10 amps DC, we got a force of about 8 newtons. So the force actually is more than sufficient to overcome the holding force. So as we slowly increase the current, as the as we cross about 5 newtons, close to about 0.5 milliseconds, the actuator starts to move. Okay, so this is really the force as a function of time. And notice that once it goes to the topmost point where we shut off the current, we still get about 5.8 newtons, which is really the holding force. One can study the velocities and accelerations as before. You can now see the center of mass movement. So you can see up to about 5 milliseconds, there is no movement in the center of mass. And then once you cross the threshold force, it moves. But still there is sufficient time now so that you can actuate it under 5 milliseconds. And you can look at the velocities as well, like before, and you can see here the velocity is still very close to 0, up to 5 milliseconds. You contrast that with what you saw earlier under constant excitation. I can compare. So the center of mass plot under this is the center of mass under pulse excitation, and if you want to compare that under constant excitation, you can do the comparison here for both of them. So we can take a look at, say, the force acting on the y-axis here, and so you can see the comparison here between the constant excitation. Here you already start with a force which is much greater, whereas in the pulse excitation it takes some time for you to achieve this force, and then they go through a same loop here. And you know, once around 0.4 milliseconds, when it reaches the maximum position, there is no need for you to have the excitation anymore, as you witness here in the pulse excitation, and you can come and get a force of 5.8 newtons. So under this new excitation motion too, one can study the flux distribution here. This is a section view of the flux. I'm going to show and one can also study the animation of how the flux is distributed as you move. So as you move the component. So, and one can also study as before the vectors here. This is under the pulse excitation mode, and you can animate the same as well. So you can see the motion is a little bit slower than before, but nevertheless it accelerates and it's able to reach its destination under 5 milliseconds. Okay, so just as a recap, let's just get back to our slide here. So we looked at a demonstration of a bistable actuator where we were able to study the response of the actuator under various excitation condition. We studied both the constant DC current condition as well as a pulse excited condition, and we were able to satisfy the design need of trying to actuate this actuator under 5 milliseconds. And in this process, we were also able to come up with the response characteristics of the actuator, namely the center of mass displacement, the velocities, the accelerations, and the force acting on the actuator at various instances of time. We were also able to establish the magnetic circuits in the form of section plots. We were able to look at the magnetic flux distribution, and we were able to animate them and see how the magnetic flux distribution changes as your component moves. Okay. So really, you can do all of this inside the SolidWorks environment using the EMS add-in. So with this, we come to an end of this webinar. I would like to thank you all for attending today's webinar. I want to remind you that a link to this recording of this webinar will be sent to you. So for people who joined in a bit late and missed the initial part of this webinar, you will be sent a link, and so you can watch them again. Please visit our website for more information about our products. And also please visit our YouTube channel so that you can get a lot of these, a lot of videos regarding our product. Also, you can access our past webinars. And for any sales related inquiries, our email address and our direct toll-free number is provided here. And finally, you will be able to download a 15-day trial version of EMS. You can go to our website and sign up for them. With that, I'm going to open up for questions and answers. So you have a chat window, and you're welcome to type in your questions, and I'll be happy to answer them here. Thank you, and have a nice day.